Dear students, welcome to Statistics and Dynamics, and thank you for tuning in to this video. This is video number 2 of lecture 4. I'm Dr. Loay Al-Zube, and we're going to continue our coverage of the content of lecture 4. We talked about the Cartesian unit vector, and we talked about that we have a general case and a special case. The special case is the unit vector is in the ijk on the Cartesian coordinate system, the xyz, and the general case is finding a unit vector for any position vector. So we're going to also introduce this concept of position vectors later on, and we will talk about those as well. We learned about the unit vectors, and we learned about the Cartesian coordinate system and the right-hand rule. So how can we represent vectors in 3 dimensions? Since the 3 components of any vector A acts on the positive I, j, k, as we talked before, we can write vector A into ax in the I direction, which is the positive x-axis, plus ay, the y component of A, in the positive y-axis, which is j, and also az, which is the z component of A, on the k direction, which is the positive z-axis. So A can be written into axi plus ayj plus azk, and this is the rectangular Cartesian representation of any vector in 3 dimensions. Separating the magnitudes, which is ax, ay, and az, and the direction ijk of each component vector will simplify the operations of vector algebra that we're going to be using. So any vector in 3 dimensions, if you are able to write it in the ajk form, which is the rectangular Cartesian coordinate system form, it will be going to be very easy for us to work with it and do all the algebraic manipulations. I want you to think of A, the vector A, consider it inside a box, and the sides of the box are this is the ax, this is the ay, and this is the az component of the vector A. In order to find these values, the ax, ay, and az, our A vector should be projected into first the z-axis. We need to have an angle, and also in order to find ax and ay, we have a 2-step process. So you need to project this vector A into the plane of the xy plane, and you will find something called A prime, and from A prime then you need to do another step to project this A prime into the x-axis and the y-axis using the Pythagorean theory that we used before. We're going to do a lot of examples about this, and we'll do a couple of exercises in the class to clarify this concept. Once you have the component ax, ay, and az, we can then find the magnitude of the vector using the Pythagorean theorem. So if you have this projection here, this is the right hand triangle, and so the magnitude of A prime is going to be ax squared plus ay squared under the square root. So the square root of ax squared plus ay squared, and that gives you this magnitude. And if you want to find the magnitude of A total using the 3 different components, ax and ay and az, you can find it by A. This is A, the magnitude is the square root of A, the x component square plus the y component square plus the z component square. It's very similar to finding the magnitude in 2 dimensions, but now because it's a 3 dimension, we have the z component to find the magnitude. And this is how you find the magnitudes of the position vector A. We calculated the magnitude. What about the direction of the Cartesian vector in 3 dimensions? So this vector A, we talked about the magnitude now, and we broke it down into components. So what about the direction? How can we identify the direction in space? We will introduce the concept of what we call the coordinate direction angles. So what are those? And there's a definition for them. We will define the direction of a vector A by the coordinate direction angles alpha, beta, and gamma. They are measured between the tail of A here and the coordinate and the positive x, y, and z axes, provided that they are located at the tail of A. So alpha is the angle between the positive x-axis and the vector A. Beta is the angle between the positive y-axis. So alpha is between these two. Beta is between the y-axis and the vector, and gamma is the angle between the z-axis and the vector itself. We know what they are. How do we calculate those angles? Because this is very important. As we said before, we have alpha, beta, and gamma, and if you look at this schematic here, See the small angle here between the x-axis and the vector, that's alpha. This one here, if you have this orangey shade, the beta is the angle between the y-axis and the vector A, and the gamma is what's represented in the green shade, is the angle between the z-axis and the vector A. And this is what we call the coordinate angles. They're measured between the vector and the x, y, and z positive axes. And they range from 0 to 180. And if we use trigonometry, so there is a formula to calculate them. So cosine alpha is going to be so remember that the vector A is represented as axi plus ayj plus azk, right? If you took the x component ax and you divided it by the magnitude of A, remember the magnitude was the square root of all of these components squared. So if you divide just the x component, just this component, and you divide by the magnitude that we calculate using this formula, you have what we call cosine alpha. Do the cosine inverse and you can get your alpha. Same thing for all the other angles, beta and gamma. You take the y component divided by the magnitude and you will end up with cosine beta. You can do the inverse, cosine inverse, and you have beta, and the same is for gamma. So this is showing you how important and how useful writing a vector in the Cartesian coordinate system is. First of all, you can see exactly what are the projections on the axis, different axes. You can represent it easily for algebraic manipulation and addition and subtraction, and also you can calculate from it if you know how to get the magnitude of that vector, the coordinate angles, which is really cool. Now these angles are not independent, they must satisfy the following rule: cosine alpha square plus cosine beta square plus cosine gamma square equals 1, and this is similar to what we have in 2 dimensions. Recall something we talked about before is called the unit vector of any position vector. So A is the vector itself divided by the magnitude. Remember, the unit vector is a vector, so it's going to end up to be having ijk. On the other hand, the magnitude is a scalar, right? So keep this in mind. So if we have the unit vector, which is a vector itself divided by the magnitude, ax divided by a, ay divided by a, and az divided by a, we have also a formula that the unit vector can be written using the cosines. So we know that ax over a is equal cosine alpha, so I can replace ax over a with cosine alpha, and ay over a with cosine beta, and az over a with cosine gamma, and then you can write your unit vector in this form. It's really very useful to be able to write any vector in the 3-dimensional Cartesian coordinate system with ijk forms. Okay, now we know how to represent a vector in Cartesian coordinate system. So we know what's components, ax, ay, and az. We learn about how to find the magnitude, which is the square root of ax squared plus ay squared plus az squared. We learned about the directional angle, coordinate directional angles, alpha, beta, and gamma. Now we can perform now the algebraic operations in 3 dimensions easily, not just in 2D. So let's start with addition, because this is important and we're going to use it many times. So if you have two vectors, let's say A and B, and you were able to write them in AX, in AY and AZ with the IJK form, I always call that Cartesian coordinate system form is the IJK form. So if you were able to write them in these forms, if you want to add these two vectors, let's say vector A and vector B, you add the X component alone, you add the Y component alone, and the Z component alone, and then you can have your vector, your resultant vector. So it's any resultant vector is summation of the different components, and you keep the directions the same in 3 dimensions. So that's how you write A, that's how you write B. You just add the X's and the Y's and the Z, and then you have your resultant if you're adding it. And if you're subtracting it, you just subtract the different components. I hope this is clear. We're going to have a lot of examples to practice doing this. Now, before we finish this lecture, I have a quick note. It's very important that sometimes the 3-dimensional vectors is given in 2 different ways. The first one is we give you the magnitude and the coordinate angles, alpha, beta, and gamma, and that's how this is the schematic, how it looked like. And sometimes we give you it in the projection angles, so magnitude and projection angles. We go alpha and theta and phi, and we're going to learn how to, this is that representation. And we will talk about the differences and how can we use either one to come up with the final format in the IJK, which is the Cartesian coordinate system or representation. So keep in mind that we are going to be jumping back and forth between these three different representations. So magnitude and coordinate angles, magnitude and projection angles, as well as this Cartesian representation. And we will do a lot of examples and homework exercises and problems to solve them in this context. Thank you for watching. Until next lecture. Bye.